this is basically a sextant. I got this from Davis Instruments. I don't know how well you guys can see it. I'm trying to see my, oh, here we go. See myself on YouTube, right? It's basically kind of like what they call like a lifeboat sextant. And it has a scale. It's like a vernier scale, but a really good and accurate one has a micrometer on there. It has filters. So basically what you're doing, the presentation will explain this, but it's a little better to see the real deal, is you look through the eyepiece here and the sun kind of comes up from, you know, some angle above, and it hits this first mirror here, and then it rockets up, and no, I know, it hits this mirror and then it rockets over here and then through. But anyways, it by this process of reflection, you're able to pick up the actual angle, and the mirror, this mirror here is only like a half a mirror. So when you look through it, you see the image of the sun in the mirror, but the other half you can see the horizon of the Earth or some reference point. So as you turn the dial, you line up the bottom of the sun typically with the horizon of the ocean. And that's basically what they call like a sight, you know. And the filters are there because usually when you look at the sun, it's really blindingly bright. So typically I put all the filters in, and then I kind of see like an orange circle on a green background that's really dark on the right side, and on the left I just see a normal, you know, like an out of doors perspective. Okay, so all right, so I'm going to roll the tape, as it were, and if this gets really, and then we'll see what we got here, you know. Okay, view. Oh, I got to share my screen. Sorry about that. Screen one. Share. Okay. And then we're going to view. Hey, okay, here we are. Okay. So I got to push a button. Okay. Yeah. So what's it about? It's about finding where you are in the globe without GPS. How did everybody figure out where they were somewhat accurately in the days before GPS? Now we kind of take it for granted. So why do you want to learn it? Well, basically it can give you a rough idea where you are, and you have a pretty good chance of getting there, especially if you're in a boat, especially. You can do it with a paper, pencil, and a sextant. A lot of people do use a calculator or an app, but it's great to know how to do it by hand in case, you know, of an emergency. Oops, I got to go back. You don't need batteries, and it's a great backup if your GPS and your iPhone go overboard. And it kind of helps you understand too, like the voyages of exploration they had, because when you see like a little bit about how they figured out where they were, it lets you understand, you know, the struggles they had to just, you know, now you just get in the jet and you go, you know, wherever you want. But, you know, finding a small island in the middle of the ocean wasn't such a simple task back then. Okay, so here's a diagram of a sextant. Here's the index mirror. This is the telescope. These are the shades that we talked about, the horizon mirror and the shade glasses. And then this is the arc. And right, this is the index bar that I was rotating back and forth, and the micrometer drum. And that's basically a typical sextant, okay? And we talked about the history of it the last time. I talked about this several years ago, but basically there's three types, at least, of position fixes I'm aware of. I'm not an expert. I'm kind of a, yeah, sort of almost a neophyte, but I'm learning some things. The three types that are really are like the noon sight of the sun. There's a method of position fix called the Mark St. Hilaire method, and there's the method of Lunars. And we'll get an explanation of what those are a little bit in the next couple slides. But a noon sight is the easiest, but you have to do it at noon. You keep in mind, if somebody's in the ocean, the weather doesn't always cooperate. It's not always clear, you know. Sometimes they go for days and it's cloudy, and then it just clears up enough to see like the sun or something. And that doesn't necessarily correspond with noon, but it is the easiest mathematically to do. The line of position fix, you can do that anytime, but it's a bit more complicated. It involves spherical trigonometry, but there are tables, and basically they've reduced it to a paper method, which is great. The lunars are even more tricky, but again, they have tables, and that's what you can do if your chronometer is basically out of whack. So now I'm gonna run a little. This is basically a small video that's going to explain a little bit about it. So I'm going to mute myself and or at least stop talking, and then we can listen to this. So
in this video, we'll explain the coordinate systems used in celestial navigation. Every location on our planet has a unique set of terrestrial coordinates consisting of latitude and longitude. These are more commonly referred to as geographic coordinates. Let's assume our planet is a perfect sphere. Latitude, marked as phi in this illustration, is the angle from the equator to the poles, from 0 to 90 degrees.
Recording in progress.
Latitude lines run parallel to the equator. Longitude, marked as gamma in this illustration, is the angle from the prime meridian, which runs through the Royal Observatory in Greenwich, England. Longitude is the angular measure on the terrestrial sphere 180 degrees west or east of the prime meridian. Latitude and longitude are both measured in degrees, arc minutes, and arc seconds, where 1 degree equals 60 arc minutes and 1 arc minute equals 60 arc seconds. There is also a coordinate system for the celestial sphere, similar to geographic latitude and longitude. Every point in the celestial sphere maps to one point on the terrestrial sphere, but due to the rotation of the Earth and the motion of the Sun, Moon, and planets, these points move in time. In navigation, the celestial coordinate system uses Greenwich hour angle and declination to describe these positions in the celestial sphere. There is a celestial equator which maps to the equator of the Earth. There is also a Greenwich celestial meridian which maps to the terrestrial prime meridian. Greenwich hour angle, abbreviated GHA, is an angular measure along the celestial equator westward from the Greenwich celestial meridian, similar to longitude. Declination, abbreviated DEC, is an angular measure north or south from the celestial equator, similar to latitude. GHA can be measured in degrees or in time, where 24 hours equals 360 degrees, hence the term hour angle. In navigation, both GHA and declination are measured in degrees, arc minutes, and arc seconds. At any given moment, every celestial body may be mapped to the Earth, as there is one point in the terrestrial sphere where the celestial body lies directly overhead. This is called the celestial body's geographic position, or GP. If you were standing at the geographic position, the celestial body would be directly overhead, known as the zenith. Measured from any point on the horizon, the angle of this celestial body would be 90 degrees. Astronavigation allows for determining your geographic position by measuring the angle from the local horizon to the celestial body and determining a line of position, which is actually a circle on the terrestrial sphere. Locally, however, these circles can be treated as straight lines. By obtaining a line of position for 2 or more celestial bodies, these lines should intersect to mark your position. This process involves knowing the geographic position of the celestial body at a given time and solving some spherical trigonometry. By using publications produced by the US Navy and their UK partners, spherical trig calculations are replaced by tables, and this process is greatly simplified. Only addition and subtraction are needed to complete a site reduction form and obtain a line of position. This concludes our video on coordinate systems. To test your understanding of what
Okay, the key thing there, I just want to go back to that
in
one.
this video,
I just want to go back to this one. Hang on, it won't let me do that. Okay. Well, anyways, the key thing there that that made it clear for me is that basically the Earth is a globe, and if you froze it at one point in time, say the sun or a star, there's one point on the Earth that's exactly straight overhead. So if you were standing at the North Pole and you looked up and Polaris was dead overhead, you know you're at the North Pole. But if you're in Fort Wayne and you look at and you see there's an angle of about 41 degrees, you know that you're not at the North Pole, but you're on a circle that goes around the Earth. And the same thing with the sun. If the sun is out there somewhere, there's a circle on the Earth. And so basically you take a fix, either two different objects or one object at different times, and those circles will intersect. So, all right, we'll go on to the next slide here. Okay, now, I'm surprised this is interleaved here. If you don't have a watch or a chronometer, there's a method called the method of Lunars that lets you find the time by measuring the position of the moon. The lunar distances were used to determine longitude from, roughly the mid to late 1700s until about 1850, because chronometers were very expensive and they just weren't widely available at a reasonable price. And Frank Reed, he's an expert in celestial navigation, shows how to calculate a lunar, and I can click on the link, and it's basically a link that shows you that you can put in your latitude, your longitude, what body you're at, and it will do the difficult task of clearing a lunar, with JavaScript. So, and here's a typical table of predicted lunar distances. I think I've skipped a couple of slides for some reason. Yes. Okay. All right. All right. Okay, back to our regularly scheduled broadcast. These next two videos will explain the method of finding your position from the noon position of the sun. So you're basically gonna watch the sun rise and fall in the sky and get its maximum height, which is local noon, and time it, and that'll tell you when noon is, and you also can get your longitude. So
Can you turn the volume up a little bit? Or I gotta crank my speaker up.
As with my other videos, I am showing practical methods of obtaining the position. There's already plenty of videos out there explaining the mathematics for anyone that wants to go into this. Firstly, the term noon position, when used in relation to celestial fixing, is usually used to refer to the taking of a sight of the sun when it is at its highest point on the sky. If we were to stand in one position on land, we would see the sun move across the sky until it was directly north or south of our position. If you've watched old Wild West movies, you'll have heard the phrase high noon. With prior to accurate timekeeping, there's actual noon at any given position. With the advent of accurate methods of timekeeping, high noon fell out of fashion, and we developed 24 different time zones for the Earth. As such, unless you're exceptionally lucky, high noon, or airpass, will never occur at noon within the time zone. So that was a very rough explanation of what Merpass is. Merpass can be used for a number of celestial bodies, but is most commonly used for the sun due to the requirement of being able to see the horizon in order to use the sextant. So what makes Merpass special? Without going into any of the complicated mathematics, as the body is true north or south of our position, we can throw all the complicated calculations out the window and remove the need to obtain multiple lines of positions to obtain our latitude. There are a couple of practical methods of calculating position at Merpass. The method I am showing does not require you to have any knowledge of your present position. To use this method, take our sextant and continuously take a sight of the celestial body. Once it reaches its highest altitude, noted by the reading starting to decrease, we note the highest reading and the time that it occurred. As I already mentioned, it's unlikely to occur at noon within your time zone, but will usually fall within an hour or two of it, so you have a rough idea of when to start taking your sight. So let's get started with our example. So we know that it's the 10th of April, 2016, and we're drifting somewhere in the North Atlantic. Using our sextant, we have been taking sights of the sun's lower limb and determined its maximum altitude was 62 degrees, 56.8 minutes, which occurred at 13, 49, and 50 seconds UTC. This figure was obtained from our sextant and is termed the sextant altitude of the sun. Before we are able to use it to obtain our latitude, we need to correct it to obtain the true altitude of the sun. In order to do this, I have provided a handy pro forma sheet for Merpass, which you can download from my website. The link is in the video description. If you followed my earlier videos, the steps for converting sextant altitude to true altitude may be familiar, as they're also on my Intercept pro forma sheet. Index error is the uncorrected error of your sextant. In most cases, unless you have dropped the sextant previously, this should be 0. Our observed altitude is the sextant altitude, corrected for index error. In our case, the index error is 0. Therefore, our observed altitude is the same as the sextant altitude. Next, we need to correct for our height above sea level, which is commonly referred to as dip on both my pro forma and in the nautical almanac. You should already know your height above sea level. If not, you'll have to work it out separately. It's good practice to always take your sights from the same position so that your height of eye above sea level is always the same. In this example, we are 20 meters above sea level. To obtain the correction, we consult table A2 at the front of the nautical almanac, where we obtain the value of 7.9. If your height of eye is not an exact value, as shown in the table, then you will have to interpolate between the values or your actual height of eye. When we subtract the dip from our observed altitude, we obtain the assumed altitude, which is referred to as apparent altitude in the British Admiralty Nautical Almanac. As our calculation is for the sun, we only require the values for the TC and arc row. In the case of the TC correction, we obtain this value from table A2, located at the front of the Nautical Almanac, and it is titled Altitude Correction Tables 10 to 90 degrees. Looking at the sun table, you'll see it split in half based on which month it is. As it's April, we look at the rightmost column of the table and we find our assumed altitude in the table. When working with this particular table, there is no need to interpolate, and we obtain the correction value of 15.5 for the sun's lower limb. The sun's lower limb is always added, whereas if we were using the sun's upper limb, we would subtract. Lastly comes the correction for non-standard conditions, which are contained in table A4, also at the front of the Nautical Almanac. Hopefully this table is self-explanatory. We're using your current temperature and air pressure, you enter the graph at the top of the page and obtain the column to use. You then enter the table below the graph and take the correction value from the table for the apparent altitude of the body. In our case, we fell within column G, so our correction is 0. Now that we know the corrections, we apply these to our assumed altitude, which gives us the true altitude of the sun as 63 degrees, 04.4 minutes. The last stage is to obtain the declination of the sun at the given time. So we turn to the daily page for the 10th of April 2016 in the Nautical Almanac. We look down the sun column, and at 1300 UTC, we obtain the declination of the sun, which is north 8 degrees, 13.6 minutes. We also make a note of the D correction value at the bottom of the column, which is 0.9. As it was 13:49 at the time of our observation, we have to correct for the 49 minutes. So we turn to the other pages at the back of the almanac and find the page for 49 minutes. We read off the correction for 0.9, which is 0.7, which we add to the declination, giving us the actual declination of north 8 degrees 14.3 minutes. Finally, to obtain the latitude, we look at the bottom table on our proforma, where we see that there is a different formula depending on our latitude, but we're working out our latitude, so how do we know which formula to use? So hopefully we know what hemisphere we're in. So if we know that we're in the northern hemisphere and our declination was south, we use the bottom formula, as the latitude and declination are considered to be named opposites. The same would apply if we were in the southern hemisphere and our declination was north. The other two formulas exist because what we do will be different depending on if we're in the tropics or not. We said we didn't know our latitude, but if you have a rough idea of what it is, then it's easy enough. If not, then a simple way of deciding if your latitude is less than the declination is to look at the sun. If from where you're standing, you're looking towards the equator, when looking at the sun, then your latitude is greater than the declination. If you're looking toward the north, when looking at the sun, in the northern hemisphere, then your latitude is probably less than the declination. In our case, the declination is less than the latitude, so we use the top formula. We take our declination, subtract the true altitude, and add 90 degrees, which gives us our latitude of 35 degrees, 09.9 minutes north. So that's how to obtain your latitude from the sun using the Merpass method. Join me next time where I'll explain a method of working out your approximate longitude at the time of Merpass. If you found this video useful, please hit the like button. My publishing schedule is a bit random due to my sea trips, so don't forget to hit subscribe if you want to be notified whenever I post a new video in my Merchant Navy how-to series. Until next time, safe sailing.
Okay. The next one is, oh, is this it? No.
Hi all, welcome back. One topic that quite a few of you have asked.
No. Okay, here's the next one. He told you how to do the longitude here. I mean, the latitude. Here's the longitude.
Hi all, and welcome back. I hope you're finding this series of videos from me useful. If there's a particular topic you want me to cover, please let me know in the comments below. In this video, which follows on from my last, I am going to cover a method of determining your approximate longitude at the time of meridian passage. I say approximate as it is unfortunately not possible to determine an exact longitude using this method. The Earth rotates on its axis at a fairly constant rate, with one full rotation taking 24 hours. As it's turning at a constant rate, it's possible to determine our position on the sphere based on a fixed point or event, which is the principle that we are using here. As we know the time of meridian passage at Greenwich, and assuming we have an accurate time that we observe meridian passage at our present location, we can use the difference between the two times to calculate our approximate longitude. Now, the reason we can only obtain an approximation is due to two things. The first is that the almanac gives the time of meridian passage as hours and minutes. Therefore, that introduces a best case accuracy of 15 nautical miles. The second issue is that as a body approaches its highest point, its change in altitude occurs very slowly, and it's simply not possible for us to accurately determine the exact time with a sextant. As such, you'll usually only have an accuracy of at least 1 minute with your own timings. Despite this, I am sure you'll agree that in a practical situation where you find yourself using the sextant and you have no alternative means, you're most likely going to be in open ocean, and an accuracy of around 15 nautical miles doesn't make a huge difference. Okay, that's enough waffling. So how do we do this? First, we need to know the time that we obtained our meridian passage reading from the sextant. Purely so that this video follows on from my previous one, we'll use the time that was used in the previous video example, which was 13:49:50 UTC on the 10th of April 2016. It's important to note that your observed time must be in UTC, not local time. Now, armed with this information, we take our nautical almanac and turn to the daily page for the 10th of April 2016. If we look at the bottom of the right-hand page, we see the time of meridian passage of the sun on the 10th of April at Greenwich is given as 12:01 UTC. As I used the meridian passage pro forma in my previous video, I'm going to continue on with it. If you haven't already done so, you might want to watch that video first. Now we take the time given in the almanac and subtract the time we observed from it, which gives us a time difference of 1 hour, 48 minutes, and 50 seconds. The last stage is to simply multiply this by 10. If you're using a calculator that accepts degrees, minutes, and seconds, it's as easy as entering the time difference, making sure you enter the hours as degrees, the minutes as minutes, and seconds as seconds, and multiplying it all by 15. Depending on your calculator, you may have to convert seconds to decimal minutes. The answer given on your calculator should come out already formatted in degrees, minutes, and seconds, which is your approximate longitude at the time of meridian passage. If your observed time of meridian passage is less than the time at Greenwich, then your longitude is east. If it's later, your longitude is west. As such, in our example, our longitude was approximately 027 degrees, 12.5 minutes west. I hope what I've explained here makes sense to you. If not, please let me know in the comments below. If you found it useful, please click the like button. And if you want to be notified when I next post a video in my Merchant Navy series, remember and subscribe, as my posting schedule is a bit random due to me being away at sea. Until next time, safe sailing.
Okay. Let's try to get to the next video. Okay. Yeah, just to summarize real quick, they have a lot of correction factors, but in essence, they find like the angle that the sun is with respect to the Earth's equator, its declination, and they subtract it from the sextant reading, and then boom, you got your latitude at noon. You don't necessarily have to have the entire nautical almanac with you. I mean, I have like a very small booklet that came with the sextant. Oh, here we go. And it's got a little table in there. It shows like that basically gives you the whole equation of time, and I think you could probably see this is a pretty small booklet, but I looked it up and it's close enough for that you're gonna end up in Florida and not in Cuba, like if you're if you're in trouble, so you don't get like Ed like that one pretty good. Yeah, so but yeah, so that's the latitude method, and then the longitude is you're basically looking at the time difference between your local solar time and Greenwich, and you're just correcting for the equation of time. It's really interesting because in the video he talks about an hour and 48 minutes. That was his difference when he was somewhere, I think in England or something. And we at StarQuest, we're roughly an hour and 48 minutes off from our time zone, or when you add the Eastern Standard. And so if you add the 60 degrees, that's the couple time zones or whatever, it basically comes out pretty close to the 86 degrees west that we're at. So you could actually use the sundial at StarQuest to roughly figure out where you are. So if you get lost, just head over to StarQuest and wait till the noon shows up on the sundial. Okay. All right, I'm now the next video is the last one we're gonna have to wade through, and it explains the what do you do if it's not noon? What do you do if you can only like look at the sun like just one time and you know roughly where you are. And so take a peek.
In this video, we'll learn how to plot a line of position. In later videos covering the site reduction form, we'll learn how to calculate the values needed in this process. But first, we'll look at how those values are used to plot a position. To chart a line of position, you'll need the following materials: a blank position plotting sheet, a parallel plotter, a compass, also known as a divider, and a pencil. Although the spacing of latitude lines is consistent throughout the globe, the spacing of longitude lines varies depending on your latitude. Near the equator, the spacing of longitude and latitude lines are equal, but as you approach either pole, longitude lines converge, narrowing as you go either north or south of the equator. To account for this, your plotting sheet has latitude lines pre-drawn but no longitude lines, which we'll need to add manually. We'll use the longitude scale in the lower right corner of the plotting sheet to get this spacing. First, we label the latitude lines in whole degrees, setting the one closest to dead reckoning in the center. Dead reckoning is simply your estimated position. In our example, let's say we're near 30 degrees north. So we label our center latitude line. As the angle increases in the northern hemisphere as we go north, we label the one above as 31 degrees north, and the one below as 29 degrees north. Note the breakdown of 60 arc minutes down the center line. 60 arc minutes equals 1 degree. Also, 1 arc minute equals 1 nautical mile, which is roughly 2,000 yards or meters. Now, we go to the longitude scale and draw a line on the nearest latitude. In our example, that's 30 degrees north. The scale is in arc minutes, and since 60 arc minutes equals 1 degree, the entire width of this scale at our latitude is the average spacing of longitude in 1 degree increments. Take your divider and set it to measure the width of 1 degree longitude. With your divider set to this distance, measure to the left and right of the center line, placing 2 or more pencil marks at each degree increment. Then, draw and label your longitude lines. In our example, let's say our nearest longitude is 60 degrees west. As west increases towards the west, or left on the sheet, we label the left one as 61 degrees west, and the right one is 59 degrees west. Let's say our dead reckoning is 30 degrees north and 12 arc minutes, and 60 degrees west and 10 arc minutes. For latitude, remember the angle increases as we go north, so our latitude coordinate is north of degree 30. Using the scale along the center line of the page, we put a mark at 12 arc minutes above 30 degrees north. For longitude, we need to use our longitude scale. It's separated in 10 arc minute increments for the first 5 sets, then in 1 or 2 increments for the last 10 arc minutes. If you needed, for example, 25 arc minutes, you'd set your divider from 20 to 0, then halfway into the 2 arc minute blocks to measure out 25. In our example, we need 10 arc minutes, so we simply measure 10 with our divider. You then move your divider to the dead reckoning mark for latitude and measure out your dead reckoning longitude. In our example, our longitude is west, so it increases to the west or left of the sheet. We put a dot in this spot and label it DR for dead reckoning. This is our estimated position. In the site reduction form, you'll pick an assumed position usable with the site reduction tables. The assumed position is often different from your dead reckoning. Let's say we have an assumed latitude of 30 degrees north, an assumed longitude of 60 degrees west, and 46.5 arc minutes. Using the same methods that we used for dead reckoning, we measure out and mark our assumed position on the chart, labeling it AP for assumed position. With our site reduction form, we'll have a celestial body with an azimuth angle calculated. We use the parallel plotter to measure that angle in the center of our sheet using this compass. Then, we'll roll the plotter to our assumed position and draw a line pointing to the celestial body. This line will run through our assumed position, pointing towards the geographic position of the celestial body. In our example, let's say the azimuth is 141.9 degrees. This gives us a line pointing to the southeast, towards the geographic position of the sun. With our site reduction form, we'll have to calculate an altitude intercept using the observed altitude, abbreviated HO, and the computed altitude, abbreviated HC. If your HO is larger than your HC, then you mark the distance towards the celestial body from your assumed position. If HO is less than HC, you mark the distance away from your assumed position. The mnemonic HO-MO-TO helps to remember this rule. In our example, let's say HO is larger than HC. So the HO-MO-TO mnemonic reminds us that we measure from the assumed position towards the celestial body. Let's say our altitude intercept is 35.9 arc minutes. So we use our divider to measure that distance using the scale on the center line and mark this position on the azimuth towards our celestial body. The line of position lies perpendicular to the azimuth at the altitude intercept. Use a ruler to draw your line of position. In our example, we see this places the line here. We label the line of position by writing the time that we took our measurement and the name of the celestial body. Also, note LL for lower limb or UL for upper limb when needed. You repeat the process with another celestial body or two, and your actual position lies where these lines of position intersect. You label that position as fix, along with the time and date you obtain the fix in parentheses. In the future, you'll calculate your next dead reckoning by estimating your speed and direction from this point and repeating the process. In this manner, you chart your position as you navigate. Note that dead reckoning is often marked by a closed half circle. Also, there are some symbols commonly used to mark your calculated positions. The US Navy, for example, uses the following guidelines. If no more than 2 lines of position were used, then this is called an estimated position, or EP, and is marked with a square. A circle is used for 3 or more lines of position and is called a fix. A triangle is used if the position was obtained electronically, such as with the GPS. This concludes our video on charting a line of position. To test your understanding of what we covered in this video, click this link. It'll take you to a few questions designed to help you remember these concepts. Once you are comfortable with this material.
Okay. I don't know if anybody noticed, but Vanderbilt University apparently has a lot of drunken sailors because they kept playing the drunken sailor tune in the background. So I thought that was kind of neat. It's probably a lot to throw at everybody right off the bat, but essentially, when you make a site, the circle on the ground is really a line on your local chart. They showed you a graphical method. You don't necessarily have to use graphical methods because, you know, we all have computers and we have apps on our phones that will do all this stuff without any problems. But this is just like what you do if you're stuck with pencil and paper, you know. So it is kind of what they used to do in the old days. It's interesting.
You can move on.
So I'm going to move on to the next. I'll try to move on.
And this.
Yay. Okay. I have a blank slide. Oh, here we go. What if you can't see the horizon? Aha. Okay. What about the guys like Lewis and Clark? And they were running around in the interior of America before it was mapped. And, you know, what if the local Indian, like what if Squanto doesn't want to tell you how to get back or something, you know? This is a problem, right? So they actually, you know, of course they made maps as they went, but they actually could, I believe they carried sextants and they could use an artificial horizon, which is, here's a picture of one. And it's a box. It's a box and it has like a pan of water And this one is really not as good as the one that I've got. I'll show you the one that I've got. This is from, it's basically a kind of a cheap little plastic box, and it's got these two filters on, but all you do is you just put water in it, and I played around with it today, and you put the water in it, and the filters keep you from getting blinded as the sun shines through. So you position it so the sun kind of goes in one and it bounces off the water and comes out, and you got to wait a couple of minutes till the vibrations settle down, but then you get a reflection of the sun. So you take your sextant and you just look at the, instead of looking at the horizon, you're looking down in the water with the sextant, but you're also getting the reflection from up in the sky, and you match them up, and you can either center them on top of each other or match the bottom of one and the top of the other. There, you can do it obviously 3 ways, but when you're done, you just take the angle if they're centered and just divide by 2. And you don't have to worry about your height above the horizon or any of that stuff. And so that's, it's that simple. It uses gravity. It's pretty cool. So that's what you do if you can't see the horizon. So, and then we talked real quickly. I'll probably go over this real quickly because I hit the wrong slide by accident. But if you don't have a watch, man, what do you mean you don't got a watch? What are you doing in this neighborhood if you don't have a watch? That was, I think Cheech and Chong had that record a long time ago. But if you don't have a watch, you're a bit hosed, but there's a way to get out of it. And you basically measure the distance of the moon to like the sun or a star or something. So instead of looking at the horizon, you use your sextant to measure the angle between one celestial body and another one. And what happens is the moon's position is different on one side of the earth or another because of parallax. And it's significant enough that with an accurate sextant, you can determine the time. I mean, it's not perfect, but for example, if you dropped your chronometer or your watch lost time, you can reset the chronometer if you didn't have any other ways to figure out your time, right? Joshua Slocum, who was, I think, the first guy to go around the world in a sailboat by himself, he used the method of lunars, I think, at one point when he was rounding the coast of South America, and he was tremendously excited that he found his position within 10 miles. So that kind of gives you an idea. The best, sextant navigator around 1900, 10 miles was like, woohoo, this is great, So and then here's just a table that just shows you, let's see, there's different times on here, and it's just interesting based on the time. As the time changes, you can see the distance between the moon and the sun changes significantly. Here's 124, 125, 127. So basically the moon and the sun are forming a clock, or the moon and something else, So, and I have some resources. This whole presentation is saved to the drive, the documents drive. I remember I sent a note around to the board, but if any of you want a pointer to the where some of these PowerPoints are, I'll shoot you a reminder. But you can look at this. But anyways, there's some really good resources. So like this will give you like a nautical almanac online. Site reduction, like they talked about here. that's a typical site reduction form to use manually. And this book I thought was actually pretty good, Celestial Navigation for the Clueless. It was pretty good, and I liked the cover art because he's got Galileo and Newton, and is that that's Newton? I think it's Galileo, maybe that's Kepler. And then there's a UFO that doesn't understand why we're using a sextant, you know. Thought that was pretty funny. But it's pretty good. The short course that we looked at some of the videos from the Vanderbilt course, but if you want to go further, it's all in there. And then there's the short course Guide to Celestial Navigation by I don't know, some guy that's I think he's German or something, but it's a really very deep. Yeah, there's the transit of Venus. Oh, you have to download it, but it's very deep. Yeah, but there's also some interesting like calculators in here. Like there's Java scripts, for example. That whole painful exercise that they showed you in the video, the site reduction, you just plug in today's date and you plug in the actual universal time, and then you tell it roughly where you are, and then you plug in your sextant readings and the temperature, and it works all of its magic, and it figures out the actual azimuth and intercept, which the intercept is the distance from your assumed position, and your azimuth is your direction. And so you can, that's a pretty good little, that's basically doing everything that the chart method did. And read navigation. This guy Frank Reed, he teaches courses, and he's over at Mystic Seaport in Connecticut. He's he even reads old logbooks from the 1850s and tries to figure out what they were talking about and stuff. So, and then I got a link to some celestial navigation calculators. So that's what I got in terms of resources. And then right now I'm basically done, and hopefully I haven't bored everyone to tears, but if you got any questions, shoot, you know.
Okay, Jim, I have a couple questions. It's Joe.
Oh boy.
Yeah, it's real simple.
Okay.
So you have a sextant, but what is the sixth part? What's in the name? Where does that come from?
Oh, I think it has to do with the angular amount of it, but it's not. They used to have a thing called an octant, and the one I've got here, which is typical, goes up to about 100 degrees. So it's not 1/6 of 360. But I don't have the answer to that right now, but I knew the answer about 2 years ago. I had a presentation and we talked about that like 2 years ago, and it's still, you know, in the can. And if you want to
ask you 2 years ago.
Yeah, you should ask me back then. You know, I got, you know, that.
All right, my bad.
Geezer disease. But yeah, basically, I think the octet was like either had less or more degrees and just didn't work out so well. And this just turned out to be the right amount of, because obviously you only need 0 to like 90, right?
Right.
But they've got a little more, you know. So.
All right. Second question.
Yeah.
This looks like it's really time and labor intensive. So how fast do you need to do this when you're on a sailing ship, for example, and how fast can you do it? Or how fast could you do it when you're at your peak?
Oh, well, I've never been at my peak because I told you I'm pretty much of a, you know, just a borderline, maybe getting out of neophyte stage, right? Because I was just interested in this, right? But I think honestly, when I had have an app that ran on my phone, and the app was free, but it's kind of out of its date range. But anyways, when I used the app, I could take a site and you press a button and it gives you the Greenwich Mean Time. It just kind of goes, zoom, you know. I could probably do it in like 4 or 5 minutes, you know. I mean, that's with one site, but if you really want to know where you are accurately, you need to kind of like make multiple sites. So you have to assume your position.
Well, all of that plotting looked like it would take a while, and you know that in the 1940s they had in the airplanes they had little bubbles for the navigators so they could see out of the airplane. I
Right.
can imagine they automated that to some extent to try to figure out where they're at before they're too far away from.
Yeah,
where
I
they
think
thought
I
they
think
were.
they right. I think you're right. I think they did have like navigation calculators and things like that. I mean, I think I showed you. Let's see, screen 2. I'll share this.
I do have a thing out of a World War II bomber, a sextant, and it's a recording sextant. You take your sighting and hit a button and it records on disk.
Oh, really? Wow.
Yeah, like here's like a site reduction JavaScript, and you just I don't know, I was messing around this. I don't know if the site's very accurate, but this is when I was, and you hit reduce site and boom, it tells you like how far. That's doing the whole plotting thing right there. But you're right, manually I think it's probably going to take about 5 or 10 minutes if you know what you're doing, because they're looking at multiple tables and stuff like that. But you know, I have the whole nautical almanac on an app in my phone, and you don't have to look up any column A and column B and index this and do that. You just say, you know, like, here's about where I am, and it says, okay, you know.
Hey, Jim.
Yeah.
I got a question.
Yeah.
Is there like a line or something you center the object? Like if you're looking at a star, would
Right.
there be an accuracy on where you put it in a circle, or how's that work?
Oh, okay. So when you look through it, let me see. I'm trying to remember if that was in one of the first videos, but it basically, you see the image of your object in the right-hand mirror.
Okay.
It's kind of, you're only see it an object in a mirror, and then the left is adjacent to it, and it's just you're looking straight at the horizon. So as you move that arm, the index arm, the position of it will move up or down in the mirror, and you just adjust it till it's right on the horizon. If it's a star, you just want it on the horizon. If it's the moon or the sun, you just want the lower part of it, the lower limb, to touch the horizon typically.
So all the tables for that are calculated on the lower target part of the target.
Yeah, you can actually do it both ways. Okay, but typically it's done with the lower limb, and that's why when he was doing the site correction, he took the number that he had off his sextant, and I think he added about 15 something arc minutes, which was the half of the diameter. That's called the SD, the semi-diameter, half of the diameter of the sun. So the sun's about 30 arc minutes, you know.
Okay.
So, yeah.
I think I'll keep using my GPS.
Well, right. I mean, sure.
Yeah,
I mean,
I might be going the wrong way or something.
and you guys haven't asked me like how accurate have I been? Well, my excuse is it's hard to find the horizon out my back door. Even when I walk over to the lake, I don't see the true horizon. However, it's probably within a good day, it's like 20 miles, maybe 30 miles, you know. So it's not like, you know, you could be in Fort Wayne or Warsaw or halfway to Fort Wayne type of thing. I think experienced navigators with good equipment, they can tell the accuracy is an arc a minute, which is basically like a mile on the instrument. But You know, they're probably like 5 miles or something if they're,
Yeah.
you know,
Hmm.
okay.
Jim, they had a thing in there, a correction factor or something there for altitude, the altitude that you're actually at. How critical was that? Do you remember that? I didn't know that was a factor.
That's basically that you want to know like how high you are, you know, like with respect to the sea level. Okay. So
Okay.
if you're standing on a boat, right?
Yeah.
Like if you're standing right on the shore of the beach, okay, and you're roughly 5.5 or 6 feet high, your eye is something like that. Okay, so your correction factor is 6 feet. But if you're like 20 feet up, the distance to the horizon goes from like 3 miles to 4 or 5 miles. So it makes a fairly big difference, you know.
Well, I'm just curious because I looked up here. If you're on land, Bear Field's at exactly 800 feet, but Smithfield is at 831.
Oh, no. I think they're talking about, right, but they're talking about if you're supposed to be doing this on a boat in the sea, and so you know your exact height of your eye above the sea, that's the horizon. But the second method that I showed you with the little pool of water, the artificial horizon, then in that case, it doesn't matter if you're on a mountain or where you are. You don't have to worry about anything because it's I don't know, it works, you know. That's all I got to say. Right? Lewis and Clark came back.
They had help.
Squanto.
Sacagawea, I think.
Yeah, something like that. Okay.
Question, have you ever read up on, this is a little off topic, but have you ever read up on surveying? How do you figure your distance when you're surveying? I guess it's a transit, isn't it? You know, now
Yeah, I know very little about it, but I do know they use like triangles, like all triangles have 180-degree internal angle, and somehow they use transit to determine you basically got one side and two angles. So angle, side, angle, that's what your geometry teacher would tell you, right?
Okay.
And
Yeah.
so they take the triangles, and I think they take a big triangle and they break them down into little dinky triangles to, you know, yeah. I would say Wikipedia, there's a good source for you.
But you know, before it was all developed and it was just raw land, like when the Lewis and Clark and the people right after them were out surveying. I
Right.
mean, and you nicely divided up your land into townships and sections and acreages and all that stuff. You know, you would think there'd be some room for some air. I'm just kind of curious if you ever.
Well, I bet you there is, but I think somehow somebody they set like different, you know, markers that, you know, they probably had a marker at every degree or something, like, which is like 60 miles or at least every time zone. And I know they have a thing called a Meridian transit telescope that they can tell the time of transit, you know, of like stars very accurately, you know. And if you get the time, you could be, you know where you are within, you know, I don't know, not as good as GPS, that's all I know. But where those stones are is where Chicago probably got laid out, man.
You just hope your meet and bound survey was accurate for your house, right?
I don't know.
That's why you got title insurance.
I mean, that's just a really good question. Is like, we take all this stuff for granted.
Yeah.
And then, you know, we're able to measure, like with GPS, that like the continents are actually moving like maybe as much as an inch a year. So what happens to that extra real estate? Do the people in New Jersey get ticked off because New Jersey's moving into like Pennsylvania, and it's Pennsylvania, like,
Yeah.
you know, does Pennsylvania get to move the borders every once in a while? I mean, in San Andreas, you can see where the roads are moving because of the fault. Well, why not Pennsylvania? Stand up for yourself, man. You know, I know they're Quakers, but come on, you know. I don't know.
That's why they use the rivers and mountains for boundaries, probably.
Yeah. But I mean, really, what happens? What's going to happen in a million years or something like that? I don't know.
Won't
Jeff
be my
Bezos will-
problem.
I don't know. I don't know.
Won't be any of our problems, will it? Yeah.
Yeah.
Well, that was interesting. Hey, if anybody has any ideas for a program or anything, get a hold of Dan. I'm sure he's going to be looking for some programs, right, Dan?
Yes, I am actively right now. That's I kind of was charting it this week.
All righty. Thank you, Dan.
I've got one I'll be submitting, so.
Okay.
There you go. You got
Yeah.
one there. All right, shake
Cool.
the tree, see what falls out.
Yeah.
And yeah, I think there's been a few times in the past where we had to go to some kind of video or something, but we try not to depend on that.
Well, I think what's well, Sarah had some really good ideas of getting hold of. There's
Speaking.
some people that would actually speak via Zoom that normally wouldn't be accessible. You know,
Yeah.
I mean, there's some resources out there, but
Yeah.
um,
Yep. There is.
I mean, I think Daniel's going to do a stellar job. I heard he's got Neil deGrasse Tyson lined up for. just
Yeah.
kidding.
I'll be
But-
interviewing him from space. I'm actually going up in the next flight. Just so
Next
you-
Blue Origin.
Yep, I'm going up. I got the 5th seat.
Yeah, there you go. You don't want the 5th seat. That's on the outside.
Right.
Yeah. Okay.
All righty. Well,
Cool. Well, I think we're good.
okay.
Yeah.
Anybody have any last words or anything?
Hope not.
Got it all out. Aired all grievances.
Solved all the world's problems, didn't we?
Right.
Well, thanks, Jim, for doing all that. Even though I was like, what the heck? I get mixed up on latitude and longitude, more or less. Which way do the lines go, this way or that way? So I'm constantly having to remember that.
I don't know. Maybe I'll go over to Connecticut and take a course because it's to me it's interesting to see
Yeah,
how
it
they
is
used to do
interesting.
stuff.
Yeah. So I guess what did the Vikings do? They just looked at stars, and the island people looked navigated by stars, right? They just say, "Oh, it's
Yeah,
over
I
that way because of the stars up there." Huh?
Yeah, I mean you can look at the altitude of the North Star and figure out your latitude pretty easily. So before they had chronometers, they would just use that and just like, well, I'm going on 35 north or 42 or something. But yeah, you're right. What did the Vikings do? I don't know, man.
Tried their best.
Yeah.
Yeah.
I mean, I think they had, before they had sextants, they had astrolabes, and they were used, and they did some, they used those basically to tell latitude, and I'm not sure if they cared about longitude as much, because if you follow a path along a coast, you just follow the same path back. But they, wasn't there some Chinese guy like about the year 900 that supposedly either circumnavigated or went around Africa or something? There's some, there were some adventurous people back in the day.
Amazing more people didn't get lost. You figure the people when they immigrated, whatever, and they sailed from Europe to here, and a lot of those journeys are like 2 months. And so if you're a little bit off and you're trying to hit New York City, and if you miss Long Island, I mean, what happened to Puritans, they were going for Virginia, weren't they? And they wound up in Massachusetts. But I mean, that's all you want is more days at sea. If you're a couple degrees off and you miss Long Island, what do you do?
Yeah.
Turn around.
Yeah.
All right. Well, I guess we had our meeting. It's about 8:49, and everybody looks so happy.
Hey, check out the smoke products on that website I sent around. They're all in color. It's pretty cool.
Smoke products?
Are they from outer space or something, or?
Yes, they are.
Oh, you sent around Gmail or something?
He sent a chat thing.
You
Oh,
see
okay.
that?
Look at the bottom. There's a
Oh,
chat.
look at that.
And we're right about here. So we got clouds and a little bit of haze and smoke, but we got more clouds coming. So
Wow.
not going to do any good. Nice clear spot, but not for tonight.
Holy moly.
I
like
gotta leave. I'm running out of power. So
Okay.
All right.
thanks for the presentation, Jim.
Yeah.
Sure, no problem.
See you, Phil.
That
Okay.
satellite came out of Fort Wayne, by the way. That's GOES 16.
Oh.
Anyway,
All right.
so I'll yield back if I can figure out how. Here we go.
So if you guys want to see what I use here, I don't to send you like to attach a link. How does one do that in the chat here?
Yeah, you can go chat. Either that or share your screen, whatever you feel, whatever you want to do.
Here, I'll just send the link so people can bookmark it because it's extremely helpful and it's in real time. It's live. It's the live satellite view over the Midwest. And so you can watch it in real time, what's happening.
Okay.
Where's chat to? Okay.
Yeah, alternate H.
And let me just make sure. Okay. So there you go.
Here it is.
This is the link that I use when I'm.
Oh yeah, College of Theater. That's more GOES and Veer's stuff. Sure.
Yep. The NT microphysics pay or like view
Oh, wow.
is perfect. I mean, it is obviously it's real time. It's only like 15 minutes behind real time, but it sees everything. So like even when there are like the thin high clouds that the radar or some other imaging things at night don't see, that just like don't show up, this will catch it. And so it's great. I will usually, when I'm imaging, I'll have one screen open with the Raspberry Pi, and then the other screen is this. So that way I can in real time see what's happening overhead.
Wow.
Yeah, that's more GOES 16 data. College of DuPage in Illinois there is one of the downlink sites, one of the main sites. There's a handful of them spread out, but they're one of them.
Yeah, I absolutely take advantage of them. They're great.
Oh, thanks for that. I got that now.
Yeah, I bookmarked that.
Okay.
But yeah, that's all I got.
Okay, everybody. I think I'm gonna call tonight myself.
All right.
All right, everybody.
Thanks later.
Yeah, hopefully we'll have Saturday. We'll have a decent night for a change this coming
I'll be out of
Saturday.
town.
Hopefully.
I'll be out of town.
Okay.
Well, if it's nice, I mean, I got family in town, but if it's nice, I might stop up. So bring them up. So
All right.
Okay.
cool.
Right.
All right. See you, everybody.
See ya.
Okay, Joe.
Bye. Take care, y'all.
Bye.